Let's move on to the another augmented data structure that is called as the segment tree. So that your interval tree is meant for answering the queries. Like these two data structures both are basically meant for you can say they are handling these data structures. So in the interval trees, we were trying to handle the queries where we were trying to find out the intersections or the overlapping ranges. So and the data when the input data was given in the form of range. So now and these segment trees basically they are on the binary trees and they are useful for handling the queries whenever you can say they are specifically meant for handling the sum queries or finding out the maximum and the minimum values from the particular range of data that is given to us, right? So here in order to let us say we are given some array, and from the array you have to find out, let us say we are given an array of size 10, and now you are given a query that you design an algorithm which can be used to find out the sum of a range from let us say 5 to 8. So this is a small array, but when we have an array of very large size, this task becomes you can say the simple algorithm that we use that becomes inefficient. So we have to find out some efficient technique or efficient data structure which can help us in getting the sum of this particular range efficiently. So in order to solve such kind of problems, we use the segment trees. So let us say the segment tree must be able to find the sum of the elements as it is said, and between the two indices. Again, that is a range from lower to left to right. So you can say the range that we have been handling in the interval trees. Now we are saying if we have to find out the sum of this range. So and also the second thing is what will happen. See, the problem comes if the array is you can say the static. That means there is no change in the array. Then again, it is okay that we can use some data structure and that can be handled. But what will happen? See, the you can say the conventional data structures that we use, they become more inefficient if the array is changing dynamically. See, what will happen if the values in the array that we have found the sum, they change. So in that case, how to handle such kind of problems? So in order to handle the you can say these two kinds of problems where the array may change dynamically, and then again we will have to redo the things that finding out the sum of that. So we are trying to find some efficient solution for solving such kind of problems, and that solution is basically the segment tree. So that segment tree is able to process both of these queries in O log n time. This is repeated by mistake. So this is one O log n time. This is not two times. So here you can see in this picture, you are shown the segment tree. So how do we create the segment tree basically? What do we do? See, but when we were working on the binary search algorithm, so what we did when we were trying to find out the searching for a number, what do we do? How do we divide that in the binary search? Yes, please. Rishabh?
Yes,
ऋषभ,
ma'am. Yes, ma'am.
बाइनरी सर्च में कैसे डिवाइड करते हैं हम?
Ma'am, binary
बाइनरी
search में
सर्च में
tree.
हमारे पास एक एरे होता है जिसको हम डिवाइड करते हैं सो दैट वी आर एबल टू फाइंड आउट द की दैट वी आर सर्चिंग फॉर.
Yes, ma'am. मैम अगर I आपका रूट नोड है तो 2i+1 आपका लेफ्ट चाइल्ड है और
हाँ
2i+2 आपका राइट चाइल्ड है.
हाँ, तो उसमें क्या है कि वी हैव डिवाइडेड दैट इनटू टू इक्वल हाफ्स, राइट? सो
Yes,
हियर
ma'am.
व्हाट वी आर डूइंग, उसमें भी हम रेंज ही बेसिकली डिवाइड करते थे, वो सॉर्टेड एरे था. But here we are not focusing on the sorting of the focusing on the sorted elements. So here we are saying that we are given an input array, and now what do we do for creating the segment tree? The complete initial array, that is, let us say if we are given an array of size 11, or you can say it is a size 10, 0 to 9. So what do? We divide that into two equal halves. So the first half becomes the left child and the second half becomes the right child. Similarly, we keep on dividing, and you can say all the ranges till we are able to reach to the individual elements of the array. So here you can see each leaf. each leaf represents one element of this particular input array, and when we combine them as we move upwards, they are combined to form a subarray, and then finally to the root nodes as we move from bottom to up, we get the complete array. Now how the segment tree will be created, that will depend. See, what kind of segment tree will be remain same, but the information that we have to store on each node, that will vary according to the problem that we are trying to solve. So here you see, this is the like creation of the binary segment tree that we create. So we assume, see, each node that we have created, after dividing the parent into two halves, that is called as the segment. So the root tree will represent the complete array, as I said. Each leaf in the segment tree will represent a single element, as I explained. So all the leaf nodes, they represent one element of the array. The internal nodes in the segment, if you want to know what is the number of internal nodes in the segment, basically that will be the union of the two elementary intervals. Here you can see that if we start from the leaf node a1 and let's say it is a0 and a1, a0 and a1, they are combined to form its parent node, that is the internal node of this segment tree. Then each vertex except the leaf node has exactly two child vertices, right, as we have seen. And this is basically, that's why this data structure is called as the segment tree. And here we are going to have, in this particular binary tree, we have exactly two child vertices. So the root of the segment tree, as I said, that represents the whole, that will be the union of all the elements. So that means it is equivalent to the given array that was initially given in order to solve the problem. When it is broken down into two halves, so we are breaking down, see here you can say we are breaking down the array as per the ranges. So the range of the for left subtree is varies from 0 to n minus 1 by 2, and the range of the right subtree, it will be from you can say the left and the right subtree. So the second one with the on the right hand side, it is going to be a n minus 1 by 2 plus 1 to n minus 1. This is the range of data. You can say, you can also say, because we are working on the array, we are our input is given in the form of array, so it is the range of the index values. So from 0 index to n minus 1 by 2 index value, all the data will be there in the left node, and from the index value n minus 1 by 2 plus 1 to n minus 1, this particular the range of index value data will be there on the in the right node. So in each segment, it is divided into half, and the two children represent the two halves. And the height of the segment tree will be log n. So there are n leaves representing the n elements of the array. So that means it is directly because each leaf has the unit element from the array. So the number of internal nodes is going to be n minus 1, and the total number of nodes is equal to 2n minus 1. So from here, see this example. So here you can see, you can count the number of leaf nodes is 1, 2, 3, 4, 5, 6. Size of the array is 7. So n minus 1 is equal to number of leaf nodes. And if you count these 1, 2, 3, so there are 13 nodes. So the total number of nodes in this particular segment tree is equal to 2 into 7, 14 minus 1, that is 13. And here you can see, when we represent the segment tree, how the data is stored in the form of the linear array. So here you can see the linear array stores the data in this particular form. Tree is the name of the array. You can say on its first index value, the range is 0 to 6, then 0 to 3, 4 to 6, 1, 2, 3. So we are the numbering that is being given over here, that represents the index value of that particular range, the way we have stored in that particular array. So this is how we create a segment tree, and now we will see how we are going to, what kind of operations that can be performed. So as I said, the once the tree is just remember that once the tree is built, we cannot change its structure. So you can say, when we are we used to do in the AVL tree and other data structures we have used, whenever performing the operations, we were allowed to change the structure of the tree. But here, the structure of the tree in the segment tree cannot be changed. The only thing that we can do is we can update the values of the nodes and query that particular tree, right? Besides that, we cannot do any kind of operation, because If we do some operation like insertion and deletion, that will change the structure of the tree, right? So here we are using, see, so that means the main objective of developing this augmented data structure is to do a special kind of task that is related to some kind of applications where we are trying to find out the sum of the range of the values, or you can say if you want to find out the maximum value in a particular range, or you want to find out the minimum value in a particular range, or you want to find out the LCM or GCD, right? Greatest common divisor, right? So such kind of special tasks are there for which we you can say special kind of applications are there, which for which these segment trees are more efficient as compared to the other data structures. So in order to see, as I said, these are more efficient in handling the updations, where the you can say the value of the arrays, the size of the array remains same, but let us say at the index value, new value has been entered. So if the new value has been entered, that means if we have to we see the sum of the array, that will change. The maximum and the minimum value of the array, that may also be changed. So in that case, the dynamic changes which are happening in the array, that can be handled using the segment tree. So now to update the element of the array and reflect the corresponding change in the segment tree, how we are going to perform that? Second thing is the query. In this operation, we can query on any interval or a segment and return the problem, let's say the maximum, minimum, or summation in the particular segment. So segment tree as how we are going to implement. So it is implemented in the form of a binary tree. So simple linear array can be used to represent the segment tree. So now the first thing that we have to see before the construction of the segment tree is what needs to be stored in the segment tree. So what needs to be stored depends upon the problem to be solved. So if the question that we are given, that we have to find out the sum, right, sum of a given range. So if the user can give us that you find out the sum of this range, so in that case, that means for while the creation of this segment tree, we are going to store the sum along with that. If the objective is to find out the maximum value of a given range, so in that case, rather than sum, we will be storing the maximum value or the minimum value. So that means while we are creating the segment tree, we have to understand what is the problem for which we are trying to create a segment tree. So how do we build a segment tree? Segment tree is built using the recursion, that is a bottom-up approach. We start with the leaves and go to the root and update the corresponding changes in the nodes that are in the path from leaves to the root. So first we create the leaves, then the two leaves combine to form the parent, and then the two parents combine to form the grandparents. So this is how we move from bottom to top. So in each step, data of the two children, that is used to form an internal parent node. You can say the merging operation is going on. If we apply the bottom up approach from the leaves to the root node, what we are doing, we are merging the two leaves to form the parent. Again, we are merging the two leaves to form the parent. So you can say each internal node, it will represent a union of its children intervals. So merging may be different for the different questions. So recursion will end up with the root node, which will represent the complete array. And for the update, what do we do? See, if there is some, because in the segment tree, we are storing the ranges. So what we have, so if there is some value change in a particular range, so what do we do? Basically, the updates, they will take place in the leaf, because leaf is storing the unit value. So we make a change in the leaf, and then from the leaf again we will move from bottom to top. And because if this a small change in the value in the change value, you can say the change in the value of the leaf will bring a change in the value of the parent also. So that means again we will be doing that recursively, that this can be done by going either to the left child or the right child, depending upon the interval that contains that particular element. So once the leaf is found, so first of all, what do we do in the updation? We move from top to bottom, because we have to update, we are given an index value whose value we have to update. So because the data is stored as per the index value range in the left and the right subtree, so first of all, if the index value lies on the left hand side, we will be traversing to the left subtree. If it is there on the right hand side, we will be traversing to the right subtree. Right. So when we are traversing through these left and right subtrees, and that case, once we have reached to the node which needs to be updated, we will be making a change in its value, and then we will have to make a change in the complete path from the leaf to the root node. Because for that range, because if we are storing the sum, the value of the sum will be changing with changing in all the ranges which are part of that. So accordingly, all the changes will be made, and this task is performed recursively. So the update will require traversing first from the top to bottom, so that we are able to find that particular leaf node, and then from bottom to up, so that we are able to update the values which are stored over there. Now, for finding out the, you can say, for executing a query on the segment, what do? We select a range, which is usually, that is the question that you are supposed to solve. So we recurse on the tree starting from the root node. Again, we check the interval that represented by the node is completely in the range from left to right. If the interval represented by the node is completely in the range from left to right, we return that node's value. So when we are executing such kind of queries, we have different kinds of cases, and according to that particular case, we have a corresponding solution. So here we say we are given the two types of queries that we can perform: update, that is given some index number and the value, update the array. That usually do. AIDX is equal to AIDX plus value. So whatever is the value, that will be updated. And when we are given a query in order to find out the range or sum of that particular range, so we are given the left and right, and we return the value of the sum of that particular range that lies within that particular. So if we have to perform these two operations using some basic algorithm, let us say we are not creating a segment tree, and we are simply applying these operations, and using the simple array operations we have done, we are performing a linear search and doing the things. So now you can say for the query, we run a loop from left to right and calculate the sum of all the elements. So each query will take O(n) time, and the update operation is going to take O(n) time. This algorithm is good, but it is good for handling the, you can say, when the amount of data that we have that is small, and the updates are, you can say, queries are very low as compared to updates in the array. But if we have, you can say, the number of queries are high, in that case we have to use the segment tree. So here you can see the build segment tree, the code for that. So how do we build? As I have already discussed, so we build node, we are taking the input as the node, the start and the end, that is the left and right range. So if start is equal to end, that means the node will have a single element, and we simply return that. Else, what do? We divide that array, right, into two halves. One is the recurse on the left child, that is build, two into node start mid, and second one is the build, that is traverse the right side. So the internal nodes will have the sum of both its children. So what is the value? So while traversing, what we are storing? The tree, that is the sum of the nodes. If the objective is, see, here is the change that you have to make. If the objective of the problem is to find out the sum, we will be storing the sum of the child nodes. If the objective is to find out the max, so we will take the max of the two child nodes. If it is the objective is to find out the mean, we will have to make only a change in this particular statement, that is tree of node is equal to tree 2 into node plus tree 2 node. So this equation will be changing depending upon the problem to be solved. So all the other parts will remain same. So here you can see, when we are given some segment tree, like we are given an array 1, 3, 5, 7, 9, 11. So here you can see what the sum of this. See, you can say the outer that we have written 0 to 5, that shows the range of data that is stored in the parent node. that is the root node, and 36 is the sum of that particular range. So the input is, so the values that we have is 6, so the range index value is from 0 to 5. So here we can see 1 plus 3 is 4, plus 5 9, plus 7 16, plus 9 uh, 25, 25 plus 11 is 36. So you can see the value is 36. If you see the, now we have driven the tree as we are creating a range. So the values of the range 0 to 2 is stored on the left hand side, and the range 3 to 5 is stored on the right hand side. Sum of the ranges 0, 1, 2, 5 plus 4, 9. So the 9 is stored, and from 7, 9, 11 the sum is 27. 27 is stored, and finally you see when we reach to the leaf nodes, the values which are being stored is 1, 3, 5, 7, 9, and 11. All the leaf nodes are having the values which are the unit values of the complete array. And this is how you can say this is the range of values that are being stored, and this is how your segment tree is being built. So this is the build process that is being shown over here, and the objective was to find out, see, when the objective is, let us say you are given a query that you have to find the, tell me the sum of the ranges from 0 to 2. So that means its value is directly you can return, that is 9. And if the value lies partially in the two, either in the left subtree or the right subtree, then what we will do, that we will discuss. Similarly, for the update operation, we can see what we are doing over here is that in the so for the update operation, what we have to do before, see, besides the ranges, we also need to have the index value and the value that we want to make a change. Let us say we want to make a change in the value of the fifth position in the array, and its new value is 10. Right? There was some old value and the new value is 10. So we need to have the index value as well as the value that we want to make a update in that particular value. So if it is the first node in the segment tree, we just update that. Otherwise, we again traverse on the left hand side and the right hand side, and we see if the start is less than equal to idx and the idx is less than equal to mid, we update. We call the update operation until we reach to that particular index value. We will keep on updating whether it is on the left hand side or the right hand side. And the internal load, see, when we are making a change, because we have done this problem for the summation, finding the sum of the query, sum of the range. So in that case, we need to apply, we need to make the changes in the, it's the update operation is not only restricted to the update, but along with that we will have to update the values of the nodes also. So like in this particular tree, so the initial values of the sum are these. If there is some change in the value, let us say the 7 is replaced by 4, so in that case the sum 16, this will be changed, then the sum 27 will be replaced, and the sum of this parent node will also be replaced. So we need to add this update operation, the sum operation again, and make a change in all the in the complete path for reaching from parent node to that leaf node. So any change in any of the unit values, that means in the leaf values, will lead to the change in the parent values also. So that's why in the update operation we need to update that particular value also. So similarly, since it was we are solving this for the addition, so in that case we are making a change in the addition. If it is the max and min, similarly the max and min will also change. We have to traverse through from the leaf to the you can say from the leaf node to the parent node, that is the root node. So for a given query, we have three conditions basically, that it may be that the range represented by node is completely inside the given range. So in that case, simply what we have to do, we have just return the range of that. So we just take to that, and then we find out the sum what is stored in that particular node, and we return that particular value. And second case may be that range represented by a node is completely outside the given range. So that means that does not exist for, and for handling that particular query, we simply return 0. That means that there is nothing like that stored over here, that is not in the range. And the range represented by a node is partially inside and partially outside the given range, then we return the sum of the left and the right child. And this the complexity of this query, you can say handling this query, is of the order of O log n, which is efficient as compared to the simple array that we have seen, that which performs this search, which performs this query in O n time. So the segment is similarly when we have to find out the sum. So when the segment is equal to the corresponding segment, the current vertex, we return the pre-computed sum that is stored in the vertex. And if it falls completely into the domain of either the left or the right child, the left child covers the segment and the right child covers the second segment. So what do? We go to the child vertex which correspond to the segment covers the query segment and execute the algorithm. That means we are able to respond to that. So, and the query segment intersects with both the children. So we cannot make recursive calls one for the child. So what we have to do, first we go to the left child, compute the partial answer for this vertex, and then we go for the right child, we compute the partial answer for that vertex, then combine the answers by adding them. And then we compute the sum query using the left and the child sum query using the right child. So that means we cannot traverse only one part, we will have to traverse on both the parts one by one if we have the partial query that is covered by both the children. So you can see the sum queries if left is greater than right. So in that case, the return 0. If left is equal to T1 and R is equal to TR, so return T of V. And the other case, what we are doing in the last case, third case, T of M is equal to T1 plus T by 2. We are dividing that into the half. And then we are moving on both, we are finding the sum of both the left as well as the right child, and we are going to return that. So here you can see this is how we perform these types of queries, and these you can see this particular pseudocode, this covers all the three cases that we have discussed. So do we have time?
No, ma'am.
Okay, so you can go through it, try to create the segment tree yourself, and we have the questions in the tute also that we can discuss tomorrow.